In case of transportation problem, we are interested in finding the minimum total cost. So all the variables given in the matrix, all the variables given in the matrix like 5, 2, 4, 3 are Cij, that is the unit cost of shipping from factory I to market J. And if all the supply and demand, that is if the total of this supply and total of this demand is equal, then the problem is said to be a balanced transportation problem. A feasible solution to a transportation problem exists only when the demand and supply are equal, that is only when the matrix is balanced. The number of basic variables in the basic feasible solution of an m into n transportation problem is m plus n minus 1. So if m plus n minus 1 equals to 0, then the basic feasible solution is degenerate, and if basic variable is 0 or positive, corresponding cell is called basic cell or occupied cell. So in case of a northwest corner cell, take the northwest value. So in this case 5 is the northwest value, so make an angle there. So now the minimum of these two, this is 22 and this is 7, so 7 is minimum, so put here 7. So now 7 is striked out. So since this is striked out, cancel this whole column. Now in this matrix, our northwest point is northwest basic value is 2, so make an angle here. Now between these two values 22 and 12, 12 is minimum, so allocate 12 here, cut out 12. In this case, since we have put 7 here, so here we decrease 7, so it becomes 15. In this case, between 15 and 12, 12 is minimum, so put 12 here, and this strike out. Since we put 12 here, so again it gets decreased to 3. Now in this matrix 4 is the cornermost point, so allocate 4 here. Then between 3 and 17, 3 is minimum, so put 3 here. Since this is 3, this strikes out, so this row will be striked out, and since we have put 3 here, it will decrease to 14. Now in this matrix 1 is the cornermost point, so make an angle here between 15 and 14. 14 is lower, so put 14 here, and here 14 gets cancelled, here it's remaining 1. Since 14 gets cancelled, so strike out this row. Now in this matrix 6 and 5, 6 is the cornermost point, so make an angle here in the 6. Now this here is 1, here is 9, 1 is lowest, so put 1 here, this goes, and this here becomes 8. Since this goes, strike out this row. Now this is the remaining one, say 8 and 8, this is equal, so our solution is correct. Now to find the total cost, we have to multiply 7 into 5 plus 12 into 2 plus 3 into 4 plus 14 into 1 plus 6 into 1 and plus 5 into 8. Here also write allocate 8. This gives our total cost. So we will be solving the same problem using least cost method. So earlier we have already told that like this 5, 2, 4, 3 are CIG, that is cost per unit. So in this method, so here we have supply, here is demand. So in this whole matrix the lowest value is 1. So in case of 1, you have to allocate. So 15 and 17, 15 is lowest, so put here 15. It goes out, here remains 2. So since it goes out, this whole column will be striked out. Now in the remaining matrix the lowest value is 2, so allocate here 12 and 22. So 12 is lowest, so 12 is gone, here 10 is remaining. Since this is gone, cancel this whole. Now in the remaining matrix 3 is the minimum value, so in 3, here is 10, here it is 9, 9 is minimum, put here 9, 9 is gone, here it is 1 remaining. Since this is gone, strike this out. Now in the remaining matrix it is 5, 4, 4, 7, 4 is minimum, so take any other 4s. So we will be taking, suppose we are taking this 4, one is minimum, so make an angle here 1, 15 and 17, 15 is minimum, so write 15. Then here is only 2 left, so strike out this. Now in this remaining matrix 2 is minimum, so mark 2. Then between 12 and 22, 12 is minimum, so write 12 here, then cut 12. 10 remains here 10. Since this is exhausted, so cut this. On the remaining matrix you have in the remaining matrix you have 3 as minimum, so mark here 3. Then between 10 and 9, 9 is minimum, so write 9. Strike this. Here only 1 is remaining. Now in this matrix there are two minimum values, 4 and 4. Since there are two minimum values, we have to allocate the one where maximum demand is fulfilling. So that is the maximum the contributed cost is maximum. So in these two cases, like here if we allot, we can allot 1 and 2, so we can allot 1 here, and in this case we can allot between 7 and 8, we can allot 7. So here the contributed cost is maximum, so we'll be allotting here. So let us put here 7, here it comes 1, here it goes completely, so since it goes, so cut this row. Now in the remaining matrix there is 4 and 7, 4 is minimum, so mark here 4. Then between 1 and 2, 1 is less, so put here 1. Then strike off this, 1 is remaining here. Now the remaining one, you can check it, 1 and 1, 1 and 1, so the question is correct. Now the total cost is 12 into 2, 1 into 4, 9 into 3, plus 5 into 1, plus 1 into 7, plus 4 into 7. This gives you least cost. Now we'll be solving the same question using Vogel's approximation method. In this method, first calculate the penalties, both row wise as well as column wise. Now the penalties are found by the difference between the lowest and the next lowest costs of every row and every column. So let us do that. In this case, if we go if we go column wise, so in this column the lowest values are 5 and 3, so the difference between 5 and 3 is 2, right here 2. Then here the lowest two values are 1 and 4, so difference is 3. Lowest is 6 and 2, difference is 4. Lowest is 4 and 4, the difference is 0. In this case the lowest is 3 and 2, so the difference is penalty is 1 here. So in this case 4 and 1 are the lowest two values, difference is 3, so 3 is the penalty. In this case 4 and 5 are the lowest two, penalty is 1. Now mark the penalty that is largest. So in this case 4 is the largest number, so target 4. Now in case of 4, it's a column penalty, so consider this corresponding column. So in this column the lowest value is 2, so here mark 2. Now between 12, remember not 4 and 1, between 12 and 22, between 12 and 22 minimum is 12, so write here 12. Again strike out, here it is 10. Since it is exhausted, cut it. Now again you have to calculate, remember again calculate the penalties, so in this case lowest two are 4 and 3, minimum is 1, so no need to write anything new. In this case 4 and 1 are minimum two values, so the penalty is 3. Same here again. In this case also the same, 5 and 4, 1. This will be same, this will be same, this will be same, and this will be exhausted, so write a mark a cross here. Now according to the new penalties, the largest penalty is this, both of these 3 and 3. Now which one to consider? Arbitrarily consider any one. So in this case let us consider, always try to in this case just use a trick, always try to exhaust the diagonal elements. So in this case 5, 8, 7, 2, 1, 5 are the diagonal elements. So in which so if you are using this or this, you are getting 1, so choose any one. So let us choose 3. So if you are choosing 3, the minimum value is 1, so mark here. Now between 15 and 17, 15 is lowest, 15 is exhausted, 2 remains. Since 15 is exhausted, cut this row. Now again calculate the penalties. So in this case penalty will be same, in this case no penalty, in this case penalty will be same, yeah. And in the row in column wise penalty will be 5 minus 3 2, 7 minus 4 3. Okay, this is sorry, here we have to take these three, as this 15 is completely exhausted. Take these three. Now again the difference is, here the difference is penalty is 3, here the penalty is 5 minus 4 1. One is the new one is the leave it as 0, leave it as 0, one is the new penalty. So next 3 is the next biggest penalty. So again go to this 4 and 7. 4 is the lowest value, so 4 is the lowest value, so mark 4. Then between 10 and 2, 2 is lowest, so to mark 2. 2 is exhausted, here it will be 8. This goes. Now the remaining are 5 3 4 5. So here the minimum is 2, penalty is 2. Again calculate the penalties. Penalty is 2, here the penalty is 1, here the penalty is 2, here the penalty is 1, same. Okay, between this 2 is the largest one, so let us take these two. Now between 3 and 5, 3 is minimum, mark 3. Then 8 and 9, 8 is minimum, so mark 8. 8 is gone, here 1 is left. Since it is gone, strike out this, so 1 is left. Now again calculate the penalties. Only one row is left, so 1 is the penalty here. In this case 5 is the new penalty, in this case 4 is the new penalty. 5 is the largest one, so take 5, only one value, pick here 1 1, so put here 1. Now only 4 is left. Now see, if when you're taking 1, then 7 is remaining. Now 7 and 7, so here automatically will become 7. So your minimum cost is 12 into 2, 12 into 4, 8 into 3, 1 into 15, 5 into 1, plus 4 into 7. After finding the initial basic feasible solution using northwest corner method or least cost method or Vogel's approximation method, we have to test the optimality. So the next step is to test whether this is optimal or not. This is done using two methods, modified distribution method, that is MODI method, or stepping stone method if the solution is not optimal. So we have obtained the VAM, initial basic feasible solution using Vogel's approximation method. So now we have to check the optimality using MODI method or stepping stone method. So in case of MODI method, we have to form cost of occupied cell and cost of unoccupied cell. So first of all, cost of occupied cell. So in this case, in the Vogel's approximation method, 2, 4, 3, 1, 4 and 5 are the cells where cost is allocated. So we will be taking only the occupied cells. So here the occupied cells are 2, 4, 3, 1, 4 and 5. So we are writing the only the occupied cells as here 2, 4, 3, here it is 1, 4 and 5. Now the rule is assign a value of 0 to any of the UI or Vj. Now UI is the variable assigned for rows. So for rows we have UI value here, for rows we have UI value, and for column we have Vj value. For column we have Vj value. So now assign any of the UI or Vj as 0 arbitrarily. So let us start from this corner. So now I have arbitrarily assigned a 0 value here. So now we have to calculate Cj equals to UI plus Vj for every cell value. So 0 plus something, so Vj is 0, 0 plus something equals to 3, 0 plus 3 equals to 3. Now move on to this 3 plus something, here is something plus 3 equals to 4, so 1 plus 3 equals to 4. Now move on to here 3 plus something equals to 2. So minus 1 plus 3 equals to 2. Now there is no value, so just move on to the next value. Here 1. So 1 plus something equals to 1.
अबे बाल क्या कुछ कर
So we can find the initial basic feasible solution using northwest corner method, least cost method, and Vogel's approximation method. Now we need to check the optimality. So after obtaining the initial basic feasible solution, the optimality can be tested by using Modi method, that is modified distribution method or stepping stone method. So now in case of Modi method, we have to arbitrarily consider a variable ui and vj for each row and column. So ui is for row and vj is for column, and now we have to assign a value of 0 to any ui or vi, and then find ui and find the value of ui and vj such that ui plus vj equals to cij for every basic solution. So next we'll find the basic feasible solution for unoccupied cells. So this is for occupied cells and this is for unoccupied cells. Now let us see how we can do that. So in Vogel's approximation method, we have find that 2, 4, 3, 1, 4 and 5, these are the occupied cells. So write the value of this in the next Modi method step. So in case of Modi methods, form two tables: cost of occupied cells, cost of unoccupied cells. So in case of cost of occupied cells, mention only the cell values which are assigned here. Like in case of VAM, 243 are assigned. So we will be mentioning only 243 here. Now this is our demand. So Vj, and this is our supply. So ui along the row. So this is our rows, and this is our ui, and this is our columns, straightwise columns, and so this is our v. Now we will be taking arbitrarily a value called 0. So let us take here 0. So now we have to make, see, ui plus vj equals to cij. This is our cij. So ui plus vj equals to cij to make. So 0 plus 3 equals to 3. 0 plus 3 equals to 3. Now move on to next one. Here it is 3. Here will be something plus 3 equals to 4. So 1 plus 3 equals to 4. Now move on to this. Minus 1 plus 3 equals to 2. Now move on to this. There is nothing, so move on to the next one. So move on to here. Just come step by step. So in this case it is 1. Here is also 1. So here would be something that gives you 1. So so 1 plus 0 becomes 1. 1 plus 0 becomes 1. Now there is no other value, so move on to the next row. So in this row, 0 plus 5 equals to 5. Now there is no other thing. Now this one, something plus 5 equals to 4. So minus 1 plus 5 equals to 4. So this is our vj and uj value. Now move on to the cost of unoccupied cells. So in this case, directly from this cell, only the vi and ui and vj values will be carried. So in this case, vj is minus 1, 1, 0, and ui is 3, 0 and 5. Now this is cost of unoccupied cell. Now move back to VAM. So what are the unoccupied cells here? 5 is unoccupied, 4 is unoccupied, 8 is unoccupied, 6, 7, 6. These are unoccupied cells. So in put only this value of unoccupied cells. So from the first row it will be 5, 4, 8, 6. So let us put it here. 5 dash, then it will be 4, 8 dash 6, 4, 8 dash 6. Next it will be 4, 6, 7 only in the middle. So dash 6, 7 dash. This is our unoccupied cells. So now in case of unoccupied cells, we have to check this formula: Cij dash equals to Cij minus Ui minus Vj. Now Cij dash is this value, Cij is our this value, from the cost of occupied cells. These values are the Cij, and sorry. So this is so we have formed the cost of unoccupied cell. Now we have to move on to net evaluation table. See, in this case, in the first cost of occupied cells, we have put the values of 2, 4, 3 from the previous VAM table of the basic cell values which are occupied. Now we have allotted UI and VJ, UI along the row, VJ along the column. So since for this column value, VJ is -1, for this column is okay. Now to now arbitrarily assign 0 to any of the Vj or ui. So let us start from here. If we put 0 here, we have to match 0 plus 5 equals to 5, then 0 plus 3 equals to 3, that is Cij equals to ui plus Vj. In case of 4, see, either it's here is this 3 here, so here we have to put 1 plus 3 equals to 4, here is 2, so -1 plus 3 equals to 2, here is 4, so 5 minus 1 equals to 4. That's it. So now from this table you will be carrying only ui vj to cost of unoccupied cell, and these values are found from the VAM method, the cell values of the unoccupied cells. Now no operation here, move on to net evaluation table. In case of net evaluation table, to find the Cij dash. Now Cij dash is found using Cij dash equals to Cij minus ui minus vj. Now Cij is here, Cij is here, these values 5, 4, 8, 6, 6, 7. So we have written down 5, 4, 8, 6, 6, 7. Now minus ui minus vj. So this is our ui, this is our vj. So minus for 5 it is -1 minus 3. So this is 3. So we will be writing all these values here. Cij, net evaluation table is formed by Cij. So this is our net evaluation table. Now in net evaluation table, yeah, now this is one more example. So in net evaluation table, if all positive, the cost is optimal. Now if see here, if all Cij dash greater than equals to 0, that is in this case these are the Cij dash in the net evaluation table. So if all Cij is greater than equals to 0, then the current solution is optimal, and if at least one of the Cij dash is less than 0, that is negative, then select the most negative variable. There may be multiple negative values, so select the most negative variable, enter an unknown quantity theta in place of the most negative value, identify a loop that starts and ends at theta, assign plus and minus theta at the corner points clockwise or anti-clockwise. So we'll check it out in the next example. When the supply and demand available are not equal, then they are called unbalanced case. In these cases, like how we should determine that, suppose in this question uh, 30 plus 55 plus 45 becomes 130, and 50 plus 40 plus 60 becomes 150. So demand and supply are not equal. So in these cases, what we need to do is we have to add a dummy row in order to accommodate this extra 20. So how we do that? In this table, we just add a dummy row here. So where to add the dummy should be a row or a column. Like in this case, this is 130. So we need to add 20 to make it equal, to make both this equal. So we have added a dummy row, and here we have added 20 excess in the supply. Now the question is, determine the optimal distribution. Since they have asked for optimal, we have to use VAM, Vogel's approximation method. So in Vogel's approximation method, what we do is first calculate the penalties row wise and column wise. So in this row, the lowest is 0, second lowest is 7, so the penalty is 7. In this, 0 is lowest, second lowest is 9, so penalty is 9 minus 0, 0. In this case 4 minus 0 4. Now row wise the penalties are 10 minus 7 3, 8 minus 7 1, then 9 minus 4 lowest 2 5, 0 minus 0 0. So now we start allocating using the Vogel's approximation method. In the whole in among all the penalties, 9 is the largest penalty. So first we take 9. Now in this row, in this column, the lowest value is 0. So accommodate 20, since 0 has 20 and 40. 20 is lowest, so accommodate 20 here. So this gets striked out only, and here 20 remains. Now we have only this much. Again calculate the penalties, don't forget, again calculate the penalties. So now if we calculate the penalties, 0, this row is gone, so now the penalties becomes 7 minus 4. In this case the penalties becomes 7 minus 4 3, so 3. In this it becomes 9 minus 10 minus 1. In this it becomes 10 minus 7 3. Similarly here also. Now again go for the lowest value and place. So in this way we find the Vogel's approximation method. Now after we find the Vogel's approximation method, always find the total cost. Total cost is 20 into 10, 5 into 7 plus 12 into 5 plus 7 into 55 plus 4 into 45. So this gives the total cost. Now after total cost, check degeneracy. How to check degeneracy? M plus n minus 1. In this case number of rows and columns are 3 and 4. So 3 plus 4 minus 1, it gives us 6. So number of how many cells are there with cost allocated? 1 2 3 4 5 6. So equals to 6. So since m plus n minus 1 equals to 6 equals to cost of table, so this is a non-degenerate problem. So in case of non-degenerate problem, directly move on to Modi method. So we check the optimality using Modi method. In case of Modi method, first calculate cost of occupied cells, cost of unoccupied cells, and then the net evaluation table. So after finding the cost of occupied cell using the Modi method, so cost of occupied cell, cost of unoccupied cell, and from there net evaluation table. So in net evaluation table, we find there is one negative value. So since there is one negative value, there is it is not an optimal solution. So what we need to do next is replace the most negative here. Replace the most negative value here. So here only one negative value is at minus 2. So replace the most negative by theta. In case of degenerate problem, you have to use epsilon. In case of degenerate problem, you have to use theta. Since it's a degenerate problem, as we have said here, since it's a non-degenerate problem, we have to use directly move on to theta. Now to replace this most negative value with theta, we have to move on to the cost matrix. So now we have written the cost matrix. So the cost matrix here comes as 5 25, then dash 55, only the cost allocated. So this is our cost matrix. So and 2 is our in this corner. So what we do is write the cost matrix. Then remember 2 was minus 2, the most negative value was here, so here we include theta. Now we have to form a loop in such a way that the loop turns only where a number is there, a number is allocated. So we have to form a loop where a number is allocated. So in this case we can easily find that the loop is forming like this. So if it comes, I can turn here but I cannot turn here, so I have to move on to this. Now I can, if there is 5, so I can turn here 20, I can turn here back to theta. So this is becoming a loop. Now always put plus in place of theta. This is plus, now this will be minus, this will be plus, this will be minus. Now in the next table, in all the cost or the numbers in the loop, 5 is the least one. So take theta equals to 5. Theta equals to 5. So since theta equals to 5, the next table is the new basic feasible solution. So new basic feasible solution becomes, so the new basic feasible solution becomes, here theta plus 5 equals to 5. Then 55 is not, so this is a turning point, so again 5, we have to operate 5, so 5 minus theta, so 5 minus theta is 5, so minus 5 minus theta is 0, so we have to put a dash here. So again 20 plus theta, so theta is 5, so 25, 20 minus theta, so 15. So this is our new feasible solution. So now we have to find the total cost of the new feasible solution. To find the total cost of from new feasible solution, we have to do 5 minus the original value. So 5 into the original value. So here 5 here 5 into 7, 25 into 10, like this. So let us do it. So calculating the total cost, we get 580. Now this 580 total cost is lesser than what the total cost we found earlier. In this case, the total cost we found was, so in this case the total cost we found was 860. So it is now optimally reduced to 850. So now again apply Modi method in this new feasible solution. So in this new feasible solution, again make the cost of occupied cell. So cost of occupied, here 5, 25 are the occupied cells. So you get the value of 7 and 10 from the very initial table. That is the initial table is here. So you get the cost of occupied cells, these 7, 10, these are the occupied ones. So here you write 7, 10, and you say all the cost of occupied 45, 85, replace them by the values from the initial table. So this is our cost of occupied cell, this is our cost of unoccupied cell. So after that, just put here 0, then 0 plus 0 should be 0, 0 plus 7, 0 plus 7 should be 7, then 0 plus 10 should be 10, and 7, it should be minus 3 plus 10 equals to 7. So in this way we have to find the values of Vj and Ui. Then directly write the values of Vj and Ui here, and fill the matrix by cost of unoccupied cells. So here these and these dashes, this dash are the unoccupied cells. So put the value of unoccupied cells from the early initial table here. So now the net evolution table is found by like 12. So 12 will be 12 minus 10 plus 0, it is 2. Then 12 again here 8 minus 3, 7, that will be 4. 9 minus 0 plus 7, so it will be 2. Similarly, we will find the net evolution table. Now since all the values in the net evolution table are positive, so the solution is optimal, and we stop here. So our total least cost is 850. So this is the case of unbalanced question. So this is the case of unbalanced case when we need to find the optimal distribution. So it is the case of unbalanced as well as degenerate case. So unbalanced as well as non-degenerate case, where m plus n minus 1 equals to 6 equals to number of the cost cells. So in case of non-degenerate, you have to use epsilon, only theta. So first find the total cost using VAM. Use the dummy if supply is not equal to demand. Then use Modi to Modi method to find the optimal solution. Now if there is all positives in the net evolution table, then it is the optimal solution, and since in this case it is not all positive, one negative is there, so this is not the optimal solution. In this case, replace the most negative value with theta. Now we have replaced the most negative value with theta in the cost matrix. So in this new matrix, we need to write the cost. So cost is like 15, 25. So our cost, replace them with the cost. So in this case, 5, 20, 15 are our cost. 5, 20, this is our cost matrix. So we have got the cost matrix. From here we have got the cost matrix. 5, 25, these allocated values are the cost. So now since we have got this minus 2 has to be replaced by theta in the cost matrix. So in the cost matrix, here we have to put theta. So what we've done, yeah, we have in the cost matrix we have put theta. Now we have to form a loop, then plus minus theta, then the 5 is the minimum value, so plus minus plus, so here 20 plus theta, here 5 plus theta, here 20 plus theta, here theta plus 5. So take the value of theta as the least value. So here 5 is the least value, so they take us to 5. So here is our new basic feasible solution. Now the new basic, now calculate the total cost of the new basic feasible solution. It should be less than the initial total cost found. Now use Modi method in the new basic feasible solution again to check the optimality. So again, cost of occupied cell, cost of unoccupied cell, net evaluation table. Now here all are positive, so it is an optimal solution. Now in the next video we will be looking on unbalanced cases with degeneracy. Now we will be solving a problem for degeneracy in transportation problem. When the number of basic variables, that is m plus n minus 1, is not equals to the number of cost allocated cells, then it is a degeneracy problem. So to get the more precise example, let us take an example. uh, so to find an optimal solution to the following TP using VAM. So this is our question. So in this case, so this is our question. We have used VAM here. So in case of VAM, Vogel's approximation method, we first find the penalties and then allocate in the least value of the maximum penalty. Take the maximum penalty. Here 2 is the maximum penalty, and in this row the least is 0, so here allocate 0, the least value of this from demand and supply. Then strike out the row that is met, and then again calculate penalty, and then again take the least value, and then again allocate and cut the row or cell. So in this way we calculate the VAM. So after you're done with VAM, the first thing we need to do is separate the cost matrix here. So we have written the cost matrix. So the cost matrix is basically comprises of the cost allocated. So here 6 2 0 6. So we've made the cost matrix. The second thing we have to do is find the total cost. So the total cost is found using 6 into 2, 2 into 2, 6 into 0 plus 6 into 2 plus 4 into 0. So we have found the total cost is 28. The third thing we need to calculate check is optimality. Before we go to check optimality using Modi method, we need to check if the solution is degenerate or non-degenerate. So if the solution is non-degenerate, then directly go for the Modi method, as we have done in the earlier cases, like this, as we have done in the earlier case. Here the solution is non-degenerate, so we have directly moved on to cost of occupied cell, so we have directly moved on to cost of occupied cell, cost of unoccupied cell, and then we've directly since in this case, since the solution was non-degenerate, we directly found we directly went for Modi method. There is no concept of epsilon. We directly went for Modi method, and in this case, when Modi method gives us negative value, we introduce theta in place of that negative value. So but in this case, we have calculated the cost matrix, we have calculated the total cost. Now as we check the degeneracy, we found that this m plus n minus 1 is not equals to the number of cost cells. So here the number of cost cells are 1 2 3 4 5, but and m plus n minus 1 is gives us 6. So these are not equal, so this is this is degenerate solution. So in case of degenerate solution, we cannot directly move on to Modi method. We have to use epsilon in the cost matrix. So we have written the cost matrix here. So we've written the cost matrix. Now we have to put epsilon in the blank spaces in such a way that epsilon doesn't form a loop. So in this case, suppose we can put anywhere, like suppose we have put epsilon here, then it is not forming a loop. See, it can go and turn here. Okay, fine. Now it cannot turn anywhere here, so it is not forming a loop. So it can go and turn here. Now there also it cannot form a loop. Now try this side. It can go here, then it can turn here, it can turn here, but it cannot turn here. Again, it can go here, it can turn here, but it cannot turn here. If you go this side, it cannot turn here. If you go this side, it cannot turn here. So this is the most suitable position. So take epsilon here. So take epsilon in such a way that it doesn't form a loop in any way. So this is a theory for epsilon. Now to solve degeneracy, we have put epsilon in any of the unoccupied cells. So this is now my new cost matrix. Now we have to conduct the Modi method. So in the case of Modi method, again cost of occupied cell, cost of unoccupied cell. So in case of cost of occupied cell, we have to calculate the values in the main table corresponding to this cost matrix. So in corresponding to 6 we have 2, then corresponding to so I have written here 2, then corresponding to epsilon we have 3, so I have written here 3. In this way I have taken the corresponding values from this table. We have written the cost of occupied cell. Now in the cost of occupied cell we will find vi, values of vi and ui. So values of vi and ui will be found will be calculated in such a way that 2 plus 0 equals 2, 2 plus 0 equals 2, then 3 plus minus 1 equals 2. So this value should be an additive of these two. Now in case of unoccupied cells, simply directly write vj and ui values here, and the values of unoccupied from here, like dash 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 are the unoccupied cells. The values corresponding to the unoccupied cells from here, you have to write it in the unoccupied cell. So in this case, after calculating the net evaluation table, the net evaluation table is 1 minus 0 plus minus 1, then 4 minus 0, then 2 minus 3 plus 0, then 3 minus 2 plus minus 1. So in this way we have calculated the net evaluation table. From the net evaluation table we don't have all the positive values. This 1 minus 1 is negative, so this we have a negative value, so this is not the optimal solution. We have to continue further. So now in case to continue the optimality check further, in case of negative values we have to include theta. Now since there is a negative value in the net evaluation table, put theta in place of that negative value in the new cost matrix. So the new cost matrix is written as it is here, and in place of that negative value minus 1 we have included theta. Now we have to form a loop such that the loop cuts only in the cell value, like from here it can cross here, from here it cannot cross here, from here it can cross here, but again it cannot cross here. So the only possible loop is theta 6 to epsilon. Now we have theta equals to theta is positive, then minus 6 will be negative, then it is positive, then again it is negative. So in this loop the lowest value is, since we have theta epsilon, you have to take theta equals to epsilon, otherwise take the lowest value in the loop. So the new basic physical solution becomes, epsilon minus epsilon 0, 2 plus epsilon, 6 minus epsilon, theta plus epsilon, and the rest is as it is. Now again use Modi method on this new basic feasible solution. Now again we have calculated the cost of occupied cell and cost of unoccupied cells and the net evaluation table. In the net evaluation table we have all the positive values, and so the solution is optimal. So in case of degeneracy, after you sort of solve the Vogel's approximation method, we have to separate the cost matrix. We have to find the total cost, and then we have to check the degeneracy. So m plus n minus 1 is not equal to the number of cost cells, so it is degenerate solution. Now without moving into Vogel's method, we have to degenerate using epsilon in the cost matrix. So this is our cost matrix. From here we got this is our cost matrix, and this cost matrix we have put epsilon in such a way that it doesn't form a loop. Then again using, now you have done the Modi method, taking theta as an occupied cell. So here we have taking epsilon as an occupied cell. So we have taken epsilon as an occupied cell. So in that way we have solved the Modi method. But again in the Modi method we have a minus 1. So since there is a minus 1, so we have to replace the most negative value by theta in the new cost matrix. So this is the new cost matrix. We have to replace this by minus 1. This minus 1 we have to replace by theta. Now in this cost matrix epsilon is also a value, theta is also a value. Now we have to form a loop such that it cuts across a number, across a cell value. So this is the only possible loop. So then plus minus theta, then take the value of theta as the least possible value. So that is epsilon. Now again plus minus epsilon in all the cases, all the that is crossed by the loop, all the cells that is caused by the loop. Now this is a new basic physical solution. Now corresponding to these values, take the values of cost of occupied cell, cost of unoccupied cell to calculate the Modi method. And now again we find the final net evolution table.